Welcome to the Lab Flow workshop. Today, we will investigate the third experiment in Lab Flow for CHEM 1412 in the Southeast Campus, which is molar mass of solute using freezing point depression. So it is my objective that at the end of this workshop, you will understand how to calculate the molar mass of the unknown using one of the colligative properties, that is freezing point depression. We will practice some problems to help you getting ready for the pre-lab quiz. Also, I will show you step by step how to plot the data in Excel and display the equation on the chart. And you will need the intersection of the two equations to calculate the freezing point. So I will share the application and I will show you how to do it. And also, in case you don't remember how to plot the data, I have written some instructions step by step that I can email it to you. So if you forgot one step, you can definitely, so if you want to write your email, I can send that set of information of how to plot the data in Excel that you will need for this experiment. So these are all the objectives. Basically, go and walk you through each step of the report, so you know how to do the report, and also to be more prepared to do the pre-lab quiz. So this is the write-up that I'm sharing of the experiment. What is interesting about colligative properties is that the changes in the physical properties between a solution and the pure solvent depends only on the number of solute particles in the solution. By now, everybody knows that. They are called colligative properties. It doesn't matter which kind of particles you dissolve in the solvent. It matters the concentration. What is the concentration of the solution? So what is this experiment about? What is the freezing point depression? It's one of the four colligative properties. What is the freezing point depression? You know what it is, the freezing point depression. It's the difference in temperature between two freezing points, the freezing point of the solvent and the freezing point of the solution. You will have a solvent, let's say in a test tube, and this will be stearic acid for our experiment. It's going to be stearic acid. So if you have stearic acid that is liquid, you warm it up and it's liquid, and then you let it cool down until it freezes. And that is the temperature of, that is the freezing temperature. We will go over that. But what happens is that if you add a non-volatile solvent, any solute, and you add here, you are going to add some solid that is an unknown. And you are going to measure the freezing point of that solution, the unknown plus the stearic acid. And then the difference between the freezing point of just the solvent and the freezing point of the solution is going to be this freezing point depression. Because it's depression, because when you add your unknown to the same solvent, the freezing point is lower. So you will have here a positive freezing point depression. So the freezing point of the solution is lower than the freezing point of the pure solvent. And here, what are they saying? I highlighted what is the most important. The freezing point depression, delta TF, is described by this equation. It says the freezing point depression equals the constant for the freezing point times the molality. This equation is for non-electrolytes, and we are going to use a non-electrolyte. Otherwise, the formula, the freezing point depression, is you have to consider the Van Hoff factor. So basically, you have to add this I, that is the Van Hoff factor. So the Kf is the freezing point depression constant. And the constant is different for each solvent. And as I just said, this I is called the Van Hoff factor. And basically, all it does is counting the number of particles. Let's say, and M, we said, is the molality with L, is the number of moles per kilogram of solvent. So all this experiment, you are going to use this formula, and all this experiment is about calculating the molar mass of an unknown. How are we going to do that? How are we going to calculate the molar mass? First thing, we are going to, from the Excel graph and from the data that is given, we are going to extract the delta TF. This is the first step. Then the second part, once we have the freezing point, we are going to calculate the molality. So the second, I will walk you through step by step, but this is just an overview so you know what are all the steps. First, from Excel, you are going to do the delta TF. You are going to, from one graph, you are going to calculate the freezing point of just the solvent. From another Excel graph, you are going to calculate the freezing point of the solution. And then, using the equation at the top, you are going to calculate delta TF. So this is the first step, and it's the most tedious step, which I will show you actually step by step how to do it. This is what it takes more time to extract the delta TF, both freezing points, and then you calculate the delta TF. Once you have that, it's two more calculations. The K is given, so you have the delta TF, you have the constant, and you are going to calculate the molality of the solute. So this is the second step, once you have the TF, the delta TF. And the last part, and then once you have the molality, you calculate the moles of the solute, because you know that the molality is the moles of the solute, the number of moles of solute per kilogram of solvent. So if you multiply the molarity here that you calculated before, and you multiply that by the mass of solvent in kilograms that is given, this is data that is going to be given, you calculate the number of moles. And the last part, you are going to, what is molar mass? Is the grams, the mass of solute in grams divided by the moles of solute. And the moles of solute comes from the previous step. And the mass of solute is given. So this is basically a quick overview of what you have to do in this experiment. And we will walk now, step by step, how to do it. So we said, let's see what else they are talking about here. Okay, here in the write-up, it says that the freezing point of the solvent and the solution will be obtained by heating the substance. Here is explaining quickly how you are going to do. So the stearic acid is our solvent, and it freezes at about 69 Celsius. So we are at about 25 degrees Celsius. So you have to heat this, you have to heat the solvent to make it liquid. And then you let it cool. You let it cool down, and you basically record while it is cooling. You will measure the temperature of the substance every 30 seconds. So here is showing the time. This is an example. It's a quick overview. It's called cooling curve. So you will have a curve. At 0, when you start, the temperature is 87 because you heat it up. This is for the solvent, and then you do the same for the solution. You do for the pure solvent a cooling curve, and you measure each 30 seconds which temperature it is when it's cooling down. At 60, and you do the same for the solution. And then you are going to plot that data. But take a look at here. For the solution, the temperature will change at very slow rate, a much slower rate than the liquid solution while freezing. But for a pure substance, like we have our pure solvent, the temperature doesn't change while it's changing the phase. But at this point, you know that during a change of phase, the temperature is constant. So what do we want to obtain from all these graphs? We want to obtain the freezing point of the pure solvent and the freezing point of the solution. So we are going to add to the pure solvent some unknown, some solid, and we are going to do the same and do the cooling curve for the solution. But notice something. Once we plot the data in Excel, you are going to see that at the beginning, let's say at the beginning, 60 seconds, 90 seconds, the temperature drops quickly. And if you look at the difference in temperature, let's say at the beginning, here, one is 82, one is 85, 3 degrees in 30 seconds. So it drops quickly, more than 0.5 Celsius between reading. But after some time, the temperature drops at much slower rate. So what you will have to do here is in Excel, that I will show you shortly, is to separate you are going to prepare two columns, two series of data, and you will have two straight lines. We will split the temperature into two columns. The first column will be the temperature reading with a difference greater than 0.5. So you're gonna do, let's say here at 120 seconds, 77.8, and then at 150, 75.3. So you do one minus the other, and if the answer is greater than 0.5, you will put that temperature in the first column. And if not, the second column is the temperature reading with a difference between two readings that is smaller than 0.5. So this is an example of what they are doing. So let's look at here, the pure solvent. The pure solvent here at 570 seconds reads 50 L Celsius. And at 600 seconds, 57.8. The difference between these two is what? It's very short. So you will put that in a second column. So this is what they are trying to explain here. So let's look at what I'm trying to tell you. When you are going to plot that data in Excel, you will do the first column is when it drops the temperature quickly, with a difference in temperature greater than 0.5 Celsius. The second column is when it drops in a slower way. Now, let's share the Excel, and I want to ask you, does everybody has Excel? Good. If not, you know I can share at the end of the session. I will stay. Definitely, if you have questions, I will stop the recording and I will stay to answer any questions. I want to make sure that after this workshop, you are ready to go and complete your report. So I wanted to let you know that. And also, you can stop me anytime. Yvonne, it says, what are your office hours? Well, you can find me in the Science Learning Center. I will be Wednesdays from 5 to 8. And also tomorrow, I will be from 6:30 to 8. And you can always email me and I will answer any questions. Okay, so, and also after the workshop, I will stay, definitely stay. Okay, so let's continue. The first thing that you have to do is plot the data in Excel. So I want to share how I do it. Okay, I hope everybody can see. So for now, I will show you how I do it, but I will email you all the steps in case you, I prepare a document with all the steps, so you don't have to memorize that. So the first thing, you know that Excel is great for plotting data, and it's a great tool for data analysis. So you are going to use this. So this, I already input the data. You know that a blank Excel spreadsheet comes like as a grid, as you see it. And we input the data in these cells, right? And we enter our data vertically in the columns. So here we have the time. and I input the data at 30 seconds, 60 seconds, 90 seconds, and I input the data vertically. And I wrote, you are going to be given this data. The only thing I did is look at that. Column B has the temperature as long as the difference between two temperatures is greater than 0.5. But now in 600, as you see here, the difference in temperature is lower than 0.5. So I started, because it's starting to cool much slower. So then I started the column C. So I will show you now. The first thing, you plot the data like that. That everybody can do, vertically. Then what do you have to do? You have to plot that data and find the intersection of the both lines, and from there you are going to find the freezing point. So we do, first we click on insert. I'm assuming everybody can see what I'm doing. Is that right?
So basically you calculated first the differences and then you plot. Is that what you did?
No, what I did is copy the data. The data is given. But at the beginning, if you look at the temperature, not the time, because the time is every 30 seconds. So I don't look at the time. I look at the temperature. And I look at two consecutive measurements. And at the beginning, the measurements, the temperature drops quickly. And the difference, let's look at the first 87.5. At 30 seconds, 85. So 87.5 minus 85, the number is greater than 0.5. So column B here, the temperature readings with difference between successive readings is higher than 0.5. And then I go down until I find that at 600, the cooling curve starts to drop in a slower manner. And then I start the column 3. Does it make sense?
Yes.
Okay, it's easier if you talk to me, because now I'm sharing the application and I don't see if you write a message. Everybody can see the Excel, right? The Excel page.
Yes.
Okay, awesome. Thank you. Yeah, it's much easier if you talk to me, because, okay. So what do we need to do? First thing, you're going to be given the data and you have to separate in column B and column C, just as I did. If two temperature readings have a difference that is lower than 0.5, you start the column C. Now we have to plot the data in order to find the intersection. So we go, click on insert, and then we always pick the scatter. The first, the first one. What does that mean? Basically, we pick a scatter plot because we want the data with no line connections to another. So this is the first thing, and you are going to see exactly this, just an empty box. And then what do? Oh, here, you click on select data. I will send you the document, so in case you forget a step. So you do select data. Very good. And then here you click on add. You are going to add the first series. And you click on here in the middle, series X values. Our X values are always the independent variable. So the temperature is always every 30 seconds and does not depend on the other. So in our case, which one is X, is the time. So we are going to highlight the time only until it starts, only until the column B ends. We start the first series when the cooling curve drops quickly. Very good. Then I put I click on the series Y value. I erase what it is in there, and I highlight the values in B, and I click OK. Now I have the first part, which is the series 1, when the temperature drops quickly. Then I have to do the same for the second part. So what do? I click on add again. I click on X, and I will do the last part of the curve. And now I will erase this, whatever is in Y, highlight the data here, and click OK. Now I have the two curves, series 1 and series 2. And I will click OK. Let's see what I have. This is the beginning of the chart. Now, the plot will not mean anything if it's not properly labeled. This is just for your future. Maybe they will accept for this report, but if you get the habit of labeling it properly, it will help you a lot. Also, look at the scale. We can change the scale because the scale starts in 0 and our values are, it starts at 50. So what do? Here, we highlight the graph. And then we go on the upper left, add chart element. And here we have everything. We have the axis. We want we have the axis titles. So let's start with that. That is easy. Let's add a title here. What is the title there? What are the units of what you are measuring down there? Let's see. What is it?
Seconds.
Exactly. So I will write time and in parentheses seconds. Very good. And then I can do the same for the vertical. And I can say time, in parentheses, the units. I can say Celsius.
You mean
Very
temperature?
good.
Isn't it temperature?
But temperature, sorry. Yes, awesome. Temperature. And actually, it came in Celsius. You can insert the little 0 for the, it doesn't come right. So let's do something else. Okay, let's do it correctly. Insert, and then we'll go to symbols, and we add this if you want to be. It doesn't have to be that perfect. And then a C. Okay, so now we have that. And we want to write also the title. So we are going to add chart title. We can say, okay, colligative properties practice. This is just a practice. Okay, and then maybe I want to change the scale. No. There are so many ways that you can do it. You can do grid lines. You can do primary minor grid lines. But the point is just to do a decent, and then, axis, no. Okay. Okay, so now, what do we want here? We want, for example, for temperature, we want a minimum of, just to look a little better. Okay, I lost the give me a second. I lost the numbers. Okay, I recovered the numbers. And now what I want is basically to format access. So what I want is the minimum temperature, instead of being 0, to be 50. And now I have a better graph. I'm just showing you that. The most important is what we need now, that is the trend line. We have to get from this graph the freezing point. In order to get the freezing point, we need to get the trend line. So we are going to find the trend line. So you are going to go to the plus. Instead of clicking here in trend line, you are going to click on the arrow, then on more options. We are going to do the series 1 first, and then we scroll down and we want to display the equation on the chart. And now this equation is the linear equation of this first part of the curve. And now we have to do the same for the second series. Okay, it's hard to see. So this is basically how you are going to plot. You put it vertically, how you are going to plot the data. And once you plot the data, I will show you how you are going to calculate the freezing point. And the freezing point is the freezing point is the intersection of both. See here. Okay, it's displaying, but I don't see the other line here. So what we want is the intersection of this linear blue with the linear orange. And that is when we are going to calculate. And I will share any questions here. I will still email you the step-by-step, but any questions on this, on how to plot the data that you are going to receive in the report?
No, so far so good.
Okay. And this is kind of what you are supposed to get. The two equations, and everybody knows now that we are looking for the intersection of these two lines, and that will be our freezing point. And we are going to do this twice. One for the pure solvent, and we are going to obtain the freezing point depression of the pure solvent. And then we are going to do the freezing point, the freezing point of the solution with the unknown. It's going to be the steric acid with the unknown. We are going to do again the same thing, the intersection of these two curves, and obtain the freezing point of the solution. And the difference between these two is going to be your delta T. So let me share another page.
So we're gonna have two graphs?
Two graphs, correct. Exactly. One is going to be for the pure solvent, and the other is going to be for the solution. And the intersection and the difference between those freezing points is going to be the delta T. So this is kind of a summary of what you are going to do after you have your graph. Let me see, I missed something. No, okay. So here, you are going to have, let's say in this case, I did it for just the pure solvent. And then you're going to repeat the same thing, the steric acid. So once you have the green, here it says cooling portion. And the red is the freezing point portion, is the one, this is the freezing point portion. The second, the one that cools down a little slower. And the cooling portion is the first part when it's still liquid and it's cooling down. And so this is what we have in the Excel. And how are you going to calculate this intersection? Well, this is math, but I just wanted to review so you remember. You know that y equals this equation. At the intersections, both y are the same, right? This is going to be the freezing temperature. This is going to be your freezing point. And the y is the same. So you equals one equation to the other. You move everything that has an x to one side of the equal, all the numbers to the other, and then you solve the equation and you get x. In my case is 506.75 seconds. But we are not that interested in this time. We are interested in the temperature of the intersection. So you take either equation. This is math, but I'm just refreshing. You take any, you can take the green or the red in order to find out the y. You solve the equation for y and you have the freezing point. Here, you take either one and you calculate the freezing point of the pure solvent. In the report, they will ask you, that's why I wrote it here, they will ask you, okay, so you remember that a linear equation equals mx plus b. So how do you call b and how do you call x? They will ask you in the report, what is the y-intercept of the freezing portion? Let's say we are doing the pure solvent. what is the y-intercept of the freezing point portion. So you will have to know, we said that the freezing portion is the one that is this one. So you will take this equation, and the y-intercept is always b. And then they will ask you, what is the slope? The slope is m. In our case, is minus 0.0005. This is the m. And the same for the other equation, for the cooling portion. They will ask you all that information. Any questions on where to get that, the y-intercept or the slope?
Not right now.
Okay, and then let me share, if this is clear, I will share. So this is kind of how is going to look your reports. Every person has a different data. So you are going to have, they are going to give you the data, and they are going to say the first cooling curve. And they are going to give you a lot of data, lots of data. And this is the data. This is how it's going to look. You will have to plot all that data in Excel. And then they will ask you, all this is how it's going to look. First, the final time to include in the cooling portion. This is what we just talked. So for the cooling curve number 1 and number 2. We discussed that. That the difference in temperature has to be lower than 0.5. And the slope of the cooling portion, this is what I just talked about. So all this is what we have seen, the slope, the y-intercept. They will ask you what is the time when the two lines intersect, and finally to calculate the freezing point. So this is all the first part of the report. And then comes when you have to do just calculations, just the calculation of the molar mass. So what are you going to do first? It says the mass of stearic acid is going to be given. They will give you, actually, you will calculate that by difference. They will tell you, okay, the mass of the test tube, beaker, and stearic acid is this, but for you, from Chem 1412, you know that that is going to be the difference between the two. And then what else? Every person has a different unknown. So this mass is one minus the other, right? Then the unknown, number 1, they will tell you how many grams of the unknown. This information, the freezing point of stearic acid, you are going to obtain it from the Excel. The freezing point of the solution, you are going to obtain it also from Excel. And the freezing point depression, which is the delta T, is going to be what? 1 minus the other, 4.77. You do the difference between the two. And then they will ask you, what is the molality of the unknown? And that's when you have to use the formula. You know that delta T equals the constant times the molality. So when you have to calculate the molality, it's going to be the molality is going to be the delta T in my case, is 4.77. This one, divided by what? The constant. The constant for that solvent is given, in my case, is 4.5 Celsius. Let me see. I guess it's 4.5. Yeah. So you obtain the molarity here. And once you have the molality, let me erase this and say that the molality is going to be your delta T divided by the constant. I'm not sure if I got the right constant, but you have it in your report. I think it is 4.5. Okay. So once you have the molality, how are you going to calculate the moles? Delta T, we said that comes from the graph, right? From the calculations and from the graph. Once we have the molality, we go for the moles. The number of moles of my unknown is going to be the molality that I calculated here times what?
Is it the kilograms of the solvent?
Yes. Awesome. Kilograms of solvent. And that is given because we know that molality is number of moles per kilogram of solvent. So that's all. This is data, this is given. And when you have to calculate the molar mass, the molar mass is the grams of the unknown that is given, that you calculated before. It's given, they give you the, let me see here, mass of the unknown is given. So in the molar mass is the grams of the unknown divided by the number of moles that you calculated here. And this is basically, the calculations are very simple, and it's more time consuming to get the freezing point and the delta T. And now I would like to share some practice before you are going to do the quiz. But do you have any questions on this, on how to do these calculations? Okay, so let me share then some practice that will help us even for the report. Let's do, to conclude, some practice. So let's see, what does it say there? What are the 4 colligative properties of these solutions? We said that colligative properties means that it doesn't matter what kind of solute, it matters only the molality, only the concentration, how many particles we have. And there are only 4. Who can tell me one?
Boiling point.
Yes, and when you say boiling point, if you memorize boiling point elevation, it will help you if you have a problem, means that the solution will have a higher boiling point than the pure solvent. Very good. Boiling point elevation is 1. Then what else? The one that we just did, freezing point depression, which means that the solution will have a lower freezing point than the pure solvent. So we have 2. Then we have the vapor pressure lowering. You probably need to remember those 4 and those 4 colligative properties. Vapor pressure lowering, we said boiling point elevation, we said freezing point depression, and we also mentioned, no, we didn't mention, and also we have the 4th one that is osmotic pressure. So those are the only 4. Let's go to the second one to refresh this. What is the definition of freezing point? Because I didn't give it to you. Is the temperature at which the liquid state changes to solid state. We kind of knew it, but we have to remember is that at this temperature, when we are at the freezing point, the solid and the liquid are in equilibrium. So that is important to remember too. Any questions? Let's try to do, yeah, let's see. Okay, let's try to do the problem number 3. Which solution will have a higher freezing point depression? A 2 molar solution of sodium chloride or a 2 molar solution of ethylene glycol? What do you think? Which one will have a higher freezing point depression? What do you think?
What's
You
the
remember,
formula for ethylene glycol?
why would that be?
What's the formula?
The formula says that the freezing point depression.
I mean, what's it called? The what's the word? Because you know it's NaCl. What's that in ethylene glycol?
That is a non-electrolyte.
Non-electrolyte. Okay.
Yeah. So the formula of delta T is the Van Hoff factor times the constant times the molality. And we know that the delta T is going to be higher if the molality is higher or the constant is higher or the Van Hoff factor is higher. The molality is the same because we have a 2 molar and a 2 molar. So we cannot count on that. The constant is the same because it depends on the solvent. So the only thing that will change is this Van Hoff factor. What is that Van Hoff factor. The freezing point depression is proportional to the Van Hoff factor. So now we need to know what is the Van Hoff factor for sodium chloride and what is the Van Hoff factor for the ethylene glycol. When we have, you are going to learn, but actually you already know, sodium chloride is an ionic compound, right? So it's going to, when you put it in the solvent, there are two ions, sodium plus chloride. That means this is one molecule, sodium chloride. So you put one here, but in water, it divides by 2. So in the water, how many particles you have on the product side?
2.
2. So the Van Hoff factor for sodium chloride is 2, because in the solution, you have 2 particles. But the ethylene glycol will not dissociate. It's not an electrolyte. So for ethylene glycol, the Van Hoff factor is just 1. So that means that which solution will have a higher freezing point depression?
NaCl?
Yes, exactly. Exactly. Because the Van Hoff factor for sodium chloride is 2. And the freezing point depression is proportional to the Van Hoff factor. Very good. Okay, so this is another thing that I wanted you to know. And here is a practice just for you. There are a few in the quiz, I think, and it will be probably beneficial for you to be able to solve a few problems like this. That's why I added this one. And after this, we are going to conclude, and I will stay to answer questions. So let's read the problem. What mass in grams of sodium chloride needs to be added to 1.5 kilograms of water to make a solution with a freezing point of minus 4.1? And they give us the freezing point depression constant of the water. They give us the value. So I usually write what I know. The solvent is water. So the constant for the water is 1.86 Celsius per molarity. So they give us that. They give us the mass of the solvent, 1.5 kilograms. And they give us the freezing point of the solution. Is minus 4.1 Celsius. So if the freezing point of the solution is minus 4.1, what is the delta T? So let's do the freezing point of the solution is minus 4.1. What is the freezing point of the solvent? Which one is the solvent?
The water.
Exactly. And what is the freezing point of the water?
0.
0. Exactly. So with these two, we know that delta T equals the freezing point, the freezing point of the solvent minus the freezing point of the solution. This is minus 4.1. This is 0. So the delta T is always positive, is 4.1 Celsius. So we have the delta T. And we can calculate.
You said it's always the solvent minus the solution?
The delta T is always positive. So for freezing point, yes, always. If we are talking about boiling point, because it's boiling point elevation, you are going to do the biggest minus the, but it doesn't matter. You have to know that is boiling point elevation, but for this experiment, yes, always. But make sure the delta T, your delta T is always positive.
Okay.
So you can do the bigger minus the smaller and you're good. Yeah. And then what do we need to do? We have the delta T. We can calculate the molality. The molality is what? The delta T divided by the Van Hoff factor divided by the constant. So our delta T is 4.1 Celsius. And what is the Van Hoff factor?
2.
2, very good. What is the value of the constant?
1.86.
Very good. So we are going to have a value for our molality that is 1.1 molar, which means 1.1 moles per kilogram of solvent. So the first step, we did the molality. Now, what do we need to do? With the molality, we can calculate the number of moles.
Yes.
Of sodium chloride. All we have to do is multiply the molality times the kilograms of solvent, that is 1.5, and we are going to have 1.65 moles of sodium chloride. But they are asking for the mass. But we have the moles. We are very close. So what do we need to do?
We need to get the molar mass of sodium.
Exactly. Exactly. So the mass that they are asking is going to be the number of moles that we calculated, 1.65 moles, times the molar mass. The molar mass, I have it.
58.5?
Okay, 58.44 grams per mole. And this is moles. So the solution for this problem, the mass, it will be 97 grams. Any questions on these problems? You can do a couple of these problems and practice. And this is basically it. We conclude this workshop now. And I hope it was helpful. And I will stop the recording, and thank you for coming, and I will stay to answer questions.